What if the universe you think you know, the one that stretches endlessly in all directions, filled with galaxies and nebulae and cosmic wonders, simply stops? What if there's an edge out there, a final boundary where reality itself ceases to exist and beyond it? Nothing? Not darkness, not emptiness, but absolute non-existence, so profound that the very concept of beyond becomes meaningless. What if every assumption we've made about infinity, about the cosmos, about our place in existence, crumbles when confronted with the possibility that space has an ending? Tonight, we venture into one of humanity's most unsettling questions, a question that has haunted philosophers for millennia and now challenges our most brilliant physicists. This isn't just academic curiosity. This is about the fundamental nature of reality itself. The idea that space might end confronts us with scenarios so alien to human intuition that our minds struggle to grasp them. An edge to the universe suggests we live in a finite container, perhaps crafted or bounded by forces we cannot comprehend. It raises the specter of walls in the cosmos, of barriers that mock our ambitions to explore, to expand, to understand. But here's what makes this question truly chilling. We might already be seeing evidence of that edge. Strange patterns in the cosmic microwave background radiation, anomalies in the distribution of galaxies, mathematical models that point toward finite geometries. All of these whisper that space might not be the infinite expanse we imagine. And if space does end, what happens at that boundary? Do the laws of physics break down? Is there a membrane separating our universe from, what? Other universes? Higher dimensions? Pure mathematical abstraction? The implications cascade outward like ripples in spacetime itself. If space is finite, then everything we know about cosmology, about the Big Bang, about the ultimate fate of the cosmos, requires revision. Our place in existence becomes even more precarious. We're not just a pale blue dot in an infinite universe, but a pale blue dot in a cosmic prison, bounded by walls we may never reach but can never escape. Yet there's something even more disturbing to consider. What if space doesn't just end? What if it ends in a way that's already determining our fate? What if the boundary of space is moving, contracting, approaching us across billions of light years? What if the edge of the universe is like a cosmic horizon that will eventually reach Earth, and when it does, space itself will cease to exist here? This isn't science fiction. It's a legitimate cosmological scenario discussed by serious physicists exploring the ultimate fate of reality. Before we dive deeper into this profound mystery, if you're fascinated by questions about the fundamental nature of reality and the cosmos, make sure to hit that subscribe button and ring the notification bell. Drop a comment below, telling me what time it is where you're watching from and where you're located. I love seeing our global community come together to explore these cosmic questions that transcend borders and time zones. And if you appreciate the research and careful consideration that goes into these deep dives into physics and cosmology, a like really helps the channel grow and reach more curious minds. Now, let's continue our journey to the possible edge of everything. Let's start with what we actually know, because in science, speculation without foundation is just fantasy, and this topic deserves better. The observable universe, the portion of space from which light has had time to reach us since the Big Bang, extends approximately 46.5 billion light years in every direction. That's the boundary of what we can see, not necessarily the boundary of what exists. This distinction is critical and bears repeating. The edge of the observable universe is not the edge of space itself, but merely the limit of our cosmic vision. The observable universe contains roughly 2 trillion galaxies, each with hundreds of billions of stars, spread across a volume so vast that human intuition fails completely when trying to grasp it. If you could travel at the speed of light, the ultimate cosmic speed limit, according to Einstein's relativity, you would need 46.5 billion years to reach the edge of what we can currently observe. And here's the kicker. Space itself is expanding, so that edge is constantly receding, moving away from us faster than light can travel. Yes, faster than light, because while nothing can move through space faster than light, space itself has no such restriction. The standard cosmological model, refined over decades of observation and calculation, suggests that space extends far beyond what we can observe. Most physicists believe the universe is either infinite or so mind-bogglingly large that the distinction barely matters for practical purposes. According to measurements of the universe's geometry, particularly from satellites like the Wilkinson Microwave Anisotropy Probe and the Planck spacecraft, space appears to be flat. In cosmological terms, flat means that parallel lines remain parallel forever, that the angles of a triangle add up to exactly 180 degrees, and most importantly, that space goes on forever in all directions. And this is where the certainty begins to crack. Those measurements have margins of error. The universe could have a very slight positive curvature, one so gentle that we cannot detect it with current instruments. If space curves back on itself like the surface of a sphere, then it would be finite but unbounded. You could travel in a straight line forever and never hit an edge. But you'd eventually return to your starting point, just as you would traveling around Earth's surface. In such a universe, space would end not with a wall or boundary, but by looping back on itself through higher dimensional geometry that our three-dimensional minds struggle to visualize. Here's what makes this question so scientifically profound. We have no direct way to measure whether space is infinite or merely unfathomably large. The observable universe is limited by the finite age of the cosmos and the speed of light. Whatever lies beyond our cosmic horizon is, by definition, beyond our ability to directly observe. We can only infer, calculate, theorize. And in that gap between observation and inference, possibility flourishes. Despite the reassuring mathematics and the observations that suggest flatness, despite the expert consensus that space likely extends infinitely, we must acknowledge the shadow of uncertainty. What if the universe is indeed finite? What if there is an edge, not in our observable region but far beyond, in the depths of space we can never see? What if the curvature is real, but so subtle that it escapes our instruments? These questions aren't idle speculation. They're legitimate scientific inquiries that challenge our understanding of reality itself. To understand whether space can end, we need to grasp the sheer scale we're dealing with. The observable universe has a diameter of approximately 93 billion light-years. 1 light-year, the distance light travels in a year, equals about 5.88 trillion miles, or 9.46 trillion kilometers. Multiply that by 93 billion, and you're looking at a distance so vast that the numbers become nearly meaningless to human cognition. We simply didn't evolve to comprehend such scales. Let's try to make this relatable, though it's a fool's errand. If you could shrink Earth to the size of a golf ball, the observable universe would extend for roughly 15 trillion miles in every direction from that golf ball. If each atom in your body represented 1 mile, you still wouldn't have enough atoms to count the miles across the observable universe. These analogies fail because the scale transcends analogy, but they hint at the magnitude we're confronting. Now consider this. The observable universe is expanding at a rate determined by the Hubble constant, currently measured at approximately 67 to 74 kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years. This means that for every 3.26 million light-years away from us an object is, it's receding at roughly 67 to 74 kilometers per second faster. At sufficient distances, this recession velocity exceeds the speed of light. Galaxies beyond a certain threshold are moving away from us so fast that light they emit today will never reach us. We are causally disconnected from them, forever separated by the expansion of space itself. The cosmic event horizon, the boundary beyond which events can never influence us because space is expanding too fast, sits at roughly 16 billion light-years away. This is different from the observable universe's edge at 46.5 billion light-years, which represents the distance light has traveled since the Big Bang. the distinction matters. We can see ancient light from regions now far beyond our event horizon, but we can never receive new information from those regions. They are, in effect, leaving our universe experientially, even though they remain part of space itself. But what if these numbers hide something more profound? What if the mathematics that describes infinite space is merely an approximation, valid in our cosmic neighborhood, but breaking down its scales far beyond observation? The possibility haunts cosmology. If space has even the slightest positive curvature, if the universe is closed rather than flat or open, then space would curve back on itself at scales potentially trillions or quadrillions of light years across. From our vantage point, such curvature would be completely undetectable, yet it would mean that space, while unimaginably vast, is ultimately finite. Current measurements suggest the universe's curvature is within 0.4% of perfectly flat. But that margin of error is crucial. A curvature of just 0.4% would still allow for a closed universe with a total diameter, perhaps 250 times larger than the observable universe. That's over 23 trillion light years across. Impossibly large by human standards, but finite nonetheless. And if space is finite, then there's a largest distance, a furthest point, an ultimate boundary to reality itself. Here's where things get genuinely weird, where the comfortable assumptions of infinite space meet observations that don't quite fit. Space isn't just about distance, it's about shape, about topology, about how it connects to itself. And we've detected anomalies. The cosmic microwave background radiation, the afterglow of the Big Bang, visible in every direction, shows unexpected patterns. It should be almost perfectly uniform, with only tiny temperature fluctuations reflecting the density variations that eventually became galaxies. And it mostly is uniform, with variations of only about 1 part in 100,000. But there are anomalies. The axis of evil, a genuinely unfortunate name for a real phenomenon. Regions where the temperature fluctuations align in ways that shouldn't happen in a truly infinite, random universe. Some scientists have proposed these alignments could indicate that the universe has a specific topology, a shape that repeats or connects to itself in unusual ways. Then there's the cold spot, a region in the cosmic microwave background that's significantly cooler than surrounding areas, larger than expected, and difficult to explain with standard cosmology. One hypothesis suggests it might be evidence of a collision between our universe and another, a bruise on the fabric of space itself. If true, this would imply that space doesn't just end, it might interface with other spaces, other universes, in ways that challenge our concept of boundaries entirely. The distribution of galaxies also shows peculiar patterns. Large-scale cosmic structures, vast filaments, and sheets of galaxies, separated by enormous voids, show alignments and periodicities that some researchers argue are inconsistent with infinite space. If space had a specific topology, if it wrapped around itself in complex ways, these patterns might be echoes of that geometry, repeated across cosmic scales as light wraps around the universe and arrives at our telescopes from multiple directions. Consider the possibility of a toroidal universe space shaped like the surface of a donut in higher dimensions. In such a universe, you could travel in one direction and eventually return to your starting point without ever encountering an edge. But you would also see peculiar patterns. The same structures might appear in multiple directions as light from them wraps around the universe. Some cosmologists have searched for such ghosts, duplicate images of galaxies, or galaxy clusters that represent the same object viewed from different light paths. So far, no confirmed detections, but the absence of evidence is not evidence of absence. This cosmological mystery opens doors to profound speculation. If space has a complex topology, it might be finite in surprising ways. You might travel forever without hitting a wall because space loops back, but the total volume could still be limited. Imagine a video game where walking off the right side of the screen brings you back on the left, The space seems continuous, but the universe is actually small and wrapping. Our cosmos might operate on similar principles, just in 3 dimensions rather than 2. But what makes these observations truly unsettling is their resistance to easy interpretation. The anomalies are statistically significant enough to demand explanation, yet subtle enough to evade definitive understanding. We're seeing hints of something patterns in the cosmic fabric that whisper about boundaries, about finite spaces, about structures beyond our ability to fully perceive. And those whispers grow louder the more carefully we listen. Let's directly address the most visceral fear. What if space has a hard edge, a boundary beyond which nothing exists? What would that mean physically? Could we reach it? What would happen if we did? First, the reassuring facts, because they matter. If space has an edge in the sense of finite volume with a specific topology, it wouldn't be a wall you could crash into. The geometry would be such that motion remains continuous. Think again of traveling on Earth's surface. You never hit an edge because the surface curves back on itself. A finite universe with closed geometry would work similarly in 3 dimensions. You'd simply arrive back where you started after traveling far enough in a straight line, never encountering any barrier. The mathematics of general relativity, Einstein's theory of gravity, and n, space-time, doesn't permit a simple edge where space suddenly stops while obeying standard physics. Space and time are woven together into space-time, and the fabric cannot just terminate abruptly without violating fundamental principles. If there were truly a boundary where space-time ended, you'd need something to enforce that boundary, some physical mechanism or principle that prevents space from extending further. Current physics provides no such mechanism. But what about more exotic scenarios? Some cosmological models suggest space could end not with a geometric closure, but with a genuine boundary where the laws of physics change. Domain walls, theoretical structures arising from phase transitions in the early universe, could represent regions where fundamental constants or even physical laws differ. Approach such a boundary, and the physics governing matter and energy might transform, making passage impossible or meaningless. Quantum field theory adds another layer. In this framework, even empty space is seething with quantum fluctuations, virtual particles constantly appearing and disappearing, fields permeating every point. For space to truly end, this quantum activity would need to cease. But what could cause such cessation? Perhaps space doesn't end sharply, but fades, becoming increasingly unstable or energetic until the concept of location loses meaning. The most realistic assessment is this: if space has an edge in any physical sense, it's so far beyond our cosmic horizon that it's not just unobservable, but causally disconnected from us. The expansion of space ensures that anything beyond our event horizon recedes from us faster than light, forever unreachable. Even if there were a boundary 100 billion light years away, we could never detect it, never reach it, never be affected by it. It would be, for all practical purposes, irrelevant to our existence. This bears repeating. The observable universe is not threatened by any edge of space. The distances involved are so vast that even if space were finite, the boundary would be impossibly remote, separated from us by expanses that dwarf our cosmic neighborhood. There is no wall approaching, no boundary closing in, no physical danger from space having limits. But what if the real worst case has nothing to do with physical edges or cosmic walls? What if the truly unsettling possibility is that space ends in a way we cannot visualize or comprehend? That the question itself is flawed because we're trying to apply 3-dimensional intuition to something fundamentally beyond human cognition? That possibility that space might end in ways our minds cannot grasp opens far more disturbing doors than any simple boundary ever could. Let's venture clearly into speculative territory now, acknowledging that what follows is conjecture built on philosophy and theoretical physics rather than direct observation. I want to be transparent. This is where we explore possibilities, not certainties. But they're possibilities worth considering, because they've been seriously discussed by scientists and philosophers. What if space ends because we exist inside a simulation, and the simulation has finite computational resources? This idea, popularized by philosopher Nick Bostrom and entertained by physicists like James Gates Jr., suggests that our universe might be a sophisticated simulation running on some substrate of reality beyond our comprehension. If true, space would necessarily be finite. The simulation would have boundaries determined by available computation. Perhaps the edge of space corresponds to the edge of the simulated region, beyond which the computation simply doesn't extend. James Gates Jr., a theoretical physicist, has pointed out that certain equations describing fundamental physics contain what look eerily like error-correcting codes, similar to those used in computer science, to maintain data integrity. While he's careful not to claim this proves we're in a simulation, he acknowledges the resemblance is striking. If our universe is computed rather than fundamental, it might have discrete rather than continuous properties at the deepest level, pixelated rather than smooth, with the smallest possible unit of space and time. In such a scenario, the universe might have a specific spatial extent beyond which the simulation doesn't bother to render anything. Like a video game that only loads the environment immediately around the player, perhaps our universe only exists in the region where conscious observers are present. Travel far enough, approach the edge of the simulated volume, and you might encounter regions where physical law breaks down simply because the computation becomes too expensive to maintain. Or perhaps you discover that distant galaxies are merely rendered facades, detailed enough to appear real when observed from afar, but lacking any genuine physical existence. This possibility aligns with certain interpretations of quantum mechanics, particularly the idea that observation creates reality. If particles exist in superposition until measured, if the wave function collapse requires consciousness or interaction, then perhaps reality itself only exists where it's being observed. The edge of space might not be a physical boundary, but an observational one-space exists where and when it's needed for the simulation to maintain consistency, and nowhere else. Critics rightfully point out that the simulation hypothesis is unfalsifiable. There's no experiment that could definitively prove or disprove it. And that's a serious philosophical problem. Science requires hypotheses that make testable predictions, that expose themselves to potential refutation. The simulation idea, while intellectually intriguing, doesn't currently offer such tests. Yet the hypothesis persists because it addresses certain puzzles. Why do the fundamental constants of nature have the specific values they do? Values that seem fine-tuned to allow complex chemistry and life. Perhaps because they were chosen by the simulation's creators. Why does quantum mechanics seem so strange, with particles existing in multiple states until observed? Perhaps because the simulation conserves computational resources by not determining outcomes until necessary. Why might space be finite? Because even the most powerful computer has limits. Speculation, yes. Unfalsifiable, certainly. But worth pondering, because it reframes the question of space's boundaries from cosmology to ontology, from the study of the universe to the study of reality itself. If space ends, perhaps it ends not at a cosmic wall, but at the limit of what's being rendered, computed, or maintained by something beyond our universe entirely. Now let's go deeper into the most dramatic what-if scenario, one that combines legitimate physics with speculative extrapolation to create a genuinely chilling possibility. This is speculation, clearly labeled as such, but it's speculation grounded in real cosmological models. What if space is finite and contracting? The universe is currently expanding, driven by dark energy, a mysterious force that constitutes roughly 68% of the total energy density of the cosmos. We observe galaxies accelerating away from each other, space itself growing larger with each passing moment. But dark energy is poorly understood. We don't know what it is, only that it's there, pushing space apart. And if we don't understand it, we cannot be certain it's permanent. Some cosmological models explore what happens if dark energy's properties change over time. If the equation of state parameter, a number describing dark energy's pressure relative to its density, shifts in specific ways, dark energy could transition from causing expansion to causing contraction. This scenario, called the Big Rip or Big Crunch depending on the specifics, would mean that the expansion of space could reverse. Now combine this with the possibility of finite space. Imagine a universe that's closed, curved back on itself, with a total volume that's large but limited. As long as expansion dominates, this curvature doesn't matter much. Space keeps growing, and any sense of boundary recedes faster than light. But if expansion reverses, if space begins to contract, then the finite nature of the cosmos becomes critical. The total volume of space would begin to shrink. The boundary, wherever and whatever it is, would approach. Picture this scenario unfolding. Billions of years from now, astronomers notice that distant galaxies are no longer red-shifted, but blue-shifted. Instead of light being stretched by expansion, it's being compressed by contraction. Space is shrinking. At first, the effect is subtle, detectable only in the most distant observations, but it accelerates. As space contracts, dark energy's influence grows, pulling space together with increasing force. What happens to matter when space itself shrinks? At first, nothing dramatic. Galaxies begin to approach each other, their separations decreasing. After many millions of years, galaxy clusters start to merge. The sky becomes brighter as galaxies, previously receding beyond visibility, come back into view. Eventually, galaxies collide more frequently, their stars mixing in cosmic chaos. But the real terror begins when space contracts to scales that affect individual solar systems. Imagine space shrinking not just between galaxies, but within them. The distance between Earth and the Sun would remain governed by gravity and orbital mechanics, but the space those orbits traverse would be changing. Physicists debate whether local structures, solar systems, planets, atoms would be torn apart or would remain intact, and the answer depends on poorly understood aspects of how dark energy interacts with matter on small scales. In some models, local structures resist the contraction until the very end. Galaxies merge into a supergalaxy, then space contracts within that structure until stars collide. Eventually, even planetary systems are disrupted. Earth might be torn from its orbit, sent careening toward the Sun, or flung into the depths of contracting space. As space continues to shrink, the very fabric of spacetime becomes distorted. Black holes grow and merge, their event horizons expanding to consume more and more matter. The end would come rapidly in cosmological terms, perhaps a few million years from when contraction affects our local region. Space would shrink to the point where even atoms cannot maintain their structure. The electromagnetic forces holding electrons in orbit around nuclei would be overwhelmed by the compression of space itself. Matter would collapse into a cosmic singularity, all of space contracting to a single point where density and temperature become infinite, where the laws of physics as we know them cease to apply. This is the Big Crunch, and in this scenario, the end of space isn't a boundary in the distance, but an endpoint in time. Space doesn't extend forever, not in spatial extent, and not in temporal duration. It ends, eventually, everywhere and all at once, collapsing back into the quantum foam from which it emerged. Constant reminder, this is speculative. Current observations show expansion accelerating, not slowing. Dark energy, as far as we can measure, seems consistent with a cosmological constant that will continue driving expansion forever. The scenarios I've described are theoretical possibilities, not predictions. They represent what could happen in alternative configurations of our universe's physical parameters, not what we expect to happen in our actual cosmos. But they're possibilities rooted in genuine physics, in models seriously considered by cosmologists, exploring the range of potential fates for the universe. This question of whether space ends connects to one of the oldest philosophical problems, the infinite regress. If space has a boundary, what lies beyond that boundary? If something lies beyond it, then space hasn't truly ended. It's just transitioned to something else. But if nothing lies beyond it, how can that be? How can there be no beyond? Our minds rebel against the concept. Ancient Greek philosophers grappled with this exact puzzle. Archytas of Tarentum posed a thought experiment around 400 BCE. Imagine standing at the edge of the universe and throwing a spear. Either the spear can continue beyond the boundary, in which case the boundary wasn't really an edge, or something stops the spear, in which case that something must exist beyond the boundary, and so the boundary, again, wasn't an edge. The logic seems inescapable. There can be no true boundary to space, because any proposed boundary must have something beyond it, even if that something is just more space. Modern physics offers a partial resolution through Einstein's general relativity. Space isn't a container that holds matter. Space and matter are intertwined. Space curves in response to mass and energy, and that curvature tells matter how to move. In this framework, space can be finite without having an edge, just as Earth's surface is finite but has no edge where you fall off. This resolves the ancient paradox by rejecting its premise. Space doesn't need a boundary that divides inside from outside, because there is no outside. A closed universe is all there is, complete unto itself. But this raises even deeper questions. If the universe is self-contained, with no outside, then what determines its properties? Why does it have the specific size, shape, and physical constants it possesses? In an infinite universe, perhaps every possible configuration exists somewhere. Making our particular region unsurprising through anthropic reasoning, we observe the conditions compatible with our existence because we couldn't exist anywhere else. But a finite universe with specific properties seems to demand explanation. This connects to the fine-tuning problem, one of the most profound puzzles in cosmology. The fundamental constants of nature, the strength of gravity, the mass of the electron, the rate of cosmic expansion, appear calibrated with extraordinary precision to allow for complex chemistry. Stars, planets, and ultimately life. Change any of these constants by a tiny fraction, and the universe becomes hostile to structure, let alone biology. If space is infinite, the multiverse hypothesis offers an explanation. Perhaps infinite universes exist, each with different constants, and we necessarily find ourselves in one of the rare examples where the constants permit observers. The vast majority of universes are sterile, but in an infinite multiverse, even the most improbable configurations occur somewhere. We observe fine-tuning, not because it's special, but because we couldn't observe anything else. But if space is finite, if our universe is all there is, then the fine-tuning becomes more mysterious. Why these specific values? Some invoke design, suggesting an intelligent creator calibrated the constants deliberately. Others propose physical principles, yet to be discovered, that make these values inevitable or natural rather than arbitrary. Still others argue the question is meaningless. The constants are simply what they are, and asking why is like asking why mathematics works. The relationship between space's boundaries and these deep questions illustrates how interconnected cosmological puzzles are. The structure of space, the nature of physical law, the possibility of other universes, all of these questions bleed into each other, forming a web of mystery that spans from the most concrete observations of distant galaxies to the most abstract philosophical inquiries into existence itself. This bears repeating. We're not just asking whether space ends. We're asking about the nature of reality, about why anything exists at all, about whether existence requires a context or whether it can be self-contained. These questions transcend science and touch on philosophy, theology, and the limits of human comprehension. And that's perhaps the most profound aspect of this inquiry. It forces us to confront how little we truly understand about the cosmos we inhabit. Let's continue exploring the philosophical implications through another angle. If space is finite, it raises profound questions about the relationship between observer and observed, between consciousness and reality. Consider a thought experiment. Imagine you're approaching the hypothetical edge of space, whatever form that might take. What would you experience? If space simply ends in the geometric sense, curving back on itself, you wouldn't notice anything special. You'd smoothly transition, moving through continuous space that happens to loop. But what if space ends in a more fundamental way? Perhaps as you approach the boundary, the resolution of reality decreases. Quantum fluctuations become larger and more prominent. The smooth continuity of space-time breaks down into discrete chunks. You're moving from the rendered region of the universe into the not yet computed, from the detailed simulation into the wireframe. Eventually, you reach a point where the concept of location becomes undefined, where space hasn't been assigned coordinates because it hasn't been generated. This connects to interpretations of quantum mechanics that grant a special role to observation. In the Copenhagen interpretation, particles don't have definite properties until measured. The wave function, a mathematical description of all possible states, collapses into a single outcome only when observed. Some physicists have suggested this means consciousness plays a fundamental role in creating reality. That observation literally brings the observed into existence. If taken to an extreme, this implies that space might only exist where it's being observed. The distant regions of the cosmos, currently unobserved by any conscious entity, might exist only as potential, as quantum superpositions of possible configurations. Send a probe or telescope that direction, and the observation would cause those regions to snap into definite existence. But in regions that will never be observed by anyone or anything, space might remain forever in superposition, existing and not existing simultaneously, all possible configurations overlaid until measurement collapses them into actuality. This sounds absurd, I know. It grants consciousness a cosmic significance that seems unjustified. A single human observer causing space itself to exist through the act of looking? How narcissistic, how anthropocentric, how philosophically suspect. And yet, quantum mechanics has repeatedly demonstrated that observation affects outcomes, that the act of measurement changes the measured system in fundamental ways. Extend this to cosmological scales, and you get observer-dependent reality, where space's extent might be tied to observation itself. The great physicist John Wheeler explored these ideas through his participatory anthropic principle. He suggested that observers are necessary to bring the universe into being, that consciousness and cosmos are mutually creating, neither fully existing without the other. In this view, the universe creates observers through evolution, and observers create the universe through observation, forming a self-consistent loop that transcends simple causality. Where does space end in such a framework? Perhaps at the boundary of observation, at the limit of what any conscious entity has witnessed or will witness. Beyond that boundary, space exists only as potential, as quantum foam pregnant with all possibilities, but manifesting none. This would make the edge of space not a physical boundary, but an epistemological one, not a limit to what is, but a limit to what can be known. But here's the truly dizzying implication. If observation creates reality, then as our civilization expands, as we send probes and telescopes to ever greater distances, we might literally be expanding space itself, not just discovering it, but creating it through the act of observation. The edge of space would be dynamic, pushed back by every new measurement, every new observation, forever receding as we chase it, but never disappearing, because there's always more potential space to collapse into actuality. This scenario makes the question, does space end, unanswerable in principle, because the answer depends on observation, and we can never observe the unobserved. It's the ultimate cosmic uncertainty principle. Asking whether space extends beyond observation is meaningless because space might only exist when observed. The question contains its own contradiction, like asking about the sound of one hand clapping or the color of numbers. Let's ground ourselves again and explore a practical question. If we definitively discovered that space is finite, what would the response be? not just scientifically, but institutionally, politically, socially. The scientific community would erupt with activity. A confirmed detection of cosmic topology, of space curving back on itself in detectable ways, would revolutionize cosmology. Research grants would flow toward understanding the specific geometry, calculating the total volume, exploring the implications for physics. The Nobel Prize would certainly go to the discovery team. Universities would create new centers for topological cosmology, bringing together mathematicians, physicists, and philosophers to explore the ramifications. But would this discovery be shared publicly? Or would there be efforts to suppress or control the information? This is where things get speculative, but worth considering. Knowledge that the universe is finite might be seen as threatening to certain worldviews or political structures. Throughout history, cosmological discoveries have met resistance when they contradicted established beliefs. Giordano Bruno was burned at the stake partly for suggesting the universe was infinite and contained countless worlds. Copernicus's heliocentric model threatened anthropocentric theology. Darwin's evolution challenged human exceptionalism. A finite universe might spark similar cultural earthquakes. Religious communities would debate the implications. Does a finite cosmos support creation narratives more strongly than an infinite one? Does it suggest intentional design, a crafted container rather than boundless chaos? Or does it diminish divine infinity, constraining God's creation to a limited space? Different traditions would reach different conclusions, and the resulting theological debates would reshape religious thought. Political responses are harder to predict. Would nations compete to be the first to fully map the universe's topology? Would space agencies pivot toward cosmological surveys rather than planetary exploration? Or would the knowledge that space has limits, that expansion beyond certain distances is fundamentally impossible, dampen enthusiasm for space exploration? If humanity can never reach beyond a finite cosmic volume, does that make the stars less inspiring or more precious? The psychological impact on the general public could be profound. Many people find comfort in the infinite, in the idea that reality extends forever, that there's always more to discover, more to explore, more room for possibility. A finite universe might feel claustrophobic, constraining, even oppressive. We'd know with certainty that there's a largest distance, a furthest place, a fundamental limit to how far we can go or what we can reach. But there might also be a strange comfort in finitude. An infinite universe can be psychologically overwhelming, rendering human existence infinitely insignificant. A finite universe, while still unimaginably vast, is at least comprehensible in principle. We could know its total extent, map its complete topology, understand its full structure. That kind of cosmic comprehensibility might appeal to our desire for boundaries and definition. The intelligence community might take interest if there were any possibility that the finite nature of space posed a security concern, perhaps, if it suggested we're in a simulation that could be modified or terminated, or if it indicated ways to manipulate spacetime that could be weaponized. While these scenarios are wildly speculative, governments have investigated stranger things. The prospect of understanding universe-scale engineering, even if only theoretically, would attract attention from those who think in terms of strategic advantage. Communication of such a discovery would be delicate. Scientists would need to carefully explain what finite means in cosmological terms, that it doesn't imply a wall or boundary that threatens us, that it's compatible with space being effectively infinite from any practical perspective. The risk of misunderstanding, of public panic or despair, would need to be managed through clear, accurate communication that respects both the evidence and people's emotional responses. But here's the grounding reality. We likely would respond with curiosity and scientific rigor, because that's how we've responded to every other cosmic discovery. When we learned Earth wasn't the center of the universe, we didn't despair. We marveled at the true scale of the cosmos. When we discovered the universe is expanding and had a beginning, we didn't collapse into nihilism. we celebrated the elegance of the Big Bang Theory. If we confirm space is finite, we'll do what humans do best. We'll study it, map it, write equations about it, and ultimately incorporate it into our evolving understanding of reality. This brings us to a crucial question about how we handle cosmological knowledge. Should there be any limits on what we investigate or publicize? Is there such a thing as dangerous cosmological knowledge? The history of science suggests that suppressing knowledge rarely works and often backfires. Attempts to constrain Copernican astronomy delayed, but didn't prevent its acceptance. Lysenko's politically motivated rejection of genetics in the Soviet Union damaged Russian biology for generations. China's initial attempts to control information about the COVID-19 outbreak allowed the pandemic to spread further than it might have otherwise. Knowledge seeks freedom, and in an interconnected world, secrets are harder to keep than ever. Moreover, cosmological knowledge seems fundamentally safe. Learning that space is finite or infinite, that the universe is open or closed, that we inhabit one of many possible geometries, none of this seems weaponizable or directly dangerous. It doesn't provide blueprints for weapons, enable exploitation of vulnerable populations, or grant power to malicious actors. It simply tells us about the structure of reality at the largest scales. Yet there's a counter-argument worth considering. If we discovered something truly unsettling, say, evidence that we're in a simulation that's scheduled to end, or that space is contracting and will eventually crush all matter out of existence, would there be value in withholding or carefully releasing such information? Would the psychological damage of hopelessness outweigh the benefits of truth? Most scientists would answer no. The value of truth, of accurate understanding of reality, outweighs the comfort of ignorance. We're better equipped to handle harsh realities when we know what they are than when we delude ourselves with false comfort. Moreover, who gets to decide what information is too dangerous? The potential for abuse in granting anyone or any institution the power to suppress knowledge is far greater than the harm that knowledge itself typically causes. The openness of modern cosmology reflects this principle. When the Planck satellite mapped the cosmic microwave background in unprecedented detail, the data was released publicly, available for anyone to analyze. When LIGO detected gravitational waves, confirming Einstein's century-old prediction, the discovery was announced globally within days. When black holes were photographed for the first time by the Event Horizon Telescope collaboration, the images became immediately public. This transparency builds trust, enables independent verification, and accelerates scientific progress. Citizen science plays an increasing role in cosmology. Projects like Galaxy Zoo allow volunteers to classify galaxies, contributing to real research. When these efforts involve millions of people examining cosmic structures, they democratize cosmology in unprecedented ways. If patterns suggesting finite space were discovered, they'd likely be found by the community of professional and amateur astronomers working collaboratively, not by a small group capable of keeping secrets. The balance, then, is between skepticism and openness. We should maintain high standards of evidence before making extraordinary claims. Not every anomaly in data represents a fundamental discovery. Most are instrumental artifacts, statistical flukes, or misinterpretations. But once evidence meets rigorous standards, it should be shared, discussed, and examined by the broadest possible community. That's how science works best, through open debate, peer review, and collective scrutiny. If we're going to err, better to err on the side of sharing too much too soon than too little too late. The worst-case scenario isn't that we learn something uncomfortable about the cosmos. It's that we allow fear of discomfort to constrain our pursuit of understanding. That path leads not to safety, but to stagnation, to a civilization that chooses comfortable ignorance over difficult truth. And that's a far greater danger than any cosmological discovery could pose. Let's step back and appreciate the sheer, incomprehensible scale of space, whether it's infinite or merely unfathomably large. This perspective is essential because it grounds our speculation in the reality of just how vast the cosmos is. The Earth is approximately 12,742 kilometers in diameter. The Moon orbits at an average distance of 384,400 kilometers away. About 30 Earths could fit in that gap. The Sun, 1.4 million kilometers across, sits 150 million kilometers away, a distance called an astronomical unit. Light takes 8 minutes and 20 seconds to cross that gap. Neptune, the most distant major planet, orbits at 30 astronomical units, about 4.5 billion kilometers from the Sun. Light takes over 4 hours to reach Neptune. But the solar system extends far beyond Neptune. The Kuiper Belt, containing Pluto and countless other icy bodies, extends to about 50 astronomical units. The scattered disk goes farther still, to perhaps 100 astronomical units. Beyond, that lies the Oort cloud, a spherical shell of comets surrounding the solar system, extending potentially 100,000 astronomical units from the Sun. That's 1.5 light years, nearly halfway to the nearest star. Proxima Centauri, our closest stellar neighbor, sits 4.24 light years away. If the Sun were a golf ball in New York City, Proxima Centauri would be another golf ball in Los Angeles. The fastest spacecraft humans have ever built, Voyager 1, traveling at 17 kilometers per second, would take over 70,000 years to reach Proxima Centauri. Space is so vast that even between the closest neighbors, the distances are nearly incomprehensible. Our Milky Way galaxy contains perhaps 400 billion stars spread across 100,000 light years. If you could travel at the speed of light, the ultimate cosmic speed limit crossing our galaxy would take 100,000 years. Radio signals we've been broadcasting since the 1930s have created a sphere of human presence, about 180 light years in diameter, a tiny bubble containing perhaps 15,000 stars within our galaxy of hundreds of billions. Most of our galaxy hasn't heard from us yet, and won't for millennia. The nearest major galaxy, Andromeda, sits 2.5 million light years away. Light that reaches us from Andromeda tonight began its journey when our hominid ancestors were just learning to use stone tools. The observable universe contains an estimated 2 trillion galaxies, each separated from others by millions or billions of light years. The total volume of space we can observe is so vast that if every star were a grain of sand, you'd need several Earth-sized planets to hold them all. And this might be just a tiny fraction of the total universe. If space is infinite, or even if it's finite, but thousands or millions of times larger than the observable region, then everything we can see is a minuscule sample, a droplet in an ocean beyond comprehension. The question of whether space ends becomes almost quaint at these scales, because the distances involved are so vast that the distinction between merely unimaginably large and truly infinite loses practical meaning. Consider the cosmic light horizon, the sphere beyond which we can never receive information because those regions are receding faster than light. This horizon represents a fundamental boundary to what we can ever know directly about the universe. Space might extend 1 trillion light years beyond that horizon, or it might curve back on itself just beyond our sight, and we currently have no way to tell. We're cosmic prisoners not of finite space, but of finite observation, trapped by the speed of light and the expansion of space. This scale humbles. Every human drama, every war and peace, every triumph and tragedy plays out on a world that's an infinitesimal speck in a galaxy that's an unremarkable member of its universe so vast that our entire cosmic neighborhood is barely a rounding error in the total. If space ends somewhere inconceivably far away, or if it continues forever, the difference to our daily lives, our civilizations, our species' history is exactly zero. We live and die in such a small corner of reality that cosmic scale structure might as well be infinite from our perspective. Yet there's strange comfort in this humility. It means our mistakes aren't cosmic catastrophes. Our failures don't ripple across reality. But neither do our achievements, which gives every accomplishment a poignant, precious quality. We matter intensely to ourselves, to those around us, to our community and planet. Beyond that, the universe continues indifferent, vast and ancient, and possibly endless, providing the stage for our small but meaningful drama. Let's shift our tone towards something more optimistic, because there's genuine reason for hope and wonder in our pursuit of these cosmic questions. The fact that we can even ask whether space ends, that we can investigate the universe's geometry with mathematics and observation, represents one of humanity's greatest achievements. Think about what we've accomplished in a cosmological eye blink. 2,000 years ago, we thought Earth was the center of everything. 500 years ago, we learned we orbit the sun. 100 years ago, we discovered our galaxy is one among billions. Within a single human lifetime, we've gone from theorizing about the Big Bang to confirming it through the cosmic microwave background, from guessing at dark matter to mapping its distribution across cosmic scales, from imagining exoplanets to cataloging thousands of them. The tools we've developed to study cosmology are marvels of human ingenuity. The Planck satellite measured temperature variations in the cosmic microwave background to 1 part in 100,000, mapping the universe as it was 380,000 years after the Big Bang. Hubble Space Telescope has looked back in time nearly to the beginning, observing galaxies whose light has traveled for 13 billion years. The James Webb Space Telescope pushes even further, revealing the earliest structures forming in the infant cosmos. Ground-based observatories, like the Atacama Large Millimeter Array, combine dozens of radio telescopes to create Ancona, instrument effectively the size of a city, resolving details impossible with any single telescope. The upcoming Vera C. Rubin Observatory will survey the entire southern sky every few nights, creating a time-lapse movie of the cosmos that will reveal how structures evolve and change. These aren't just scientific instruments, they're monuments to human curiosity, to our refusal to accept ignorance when understanding is possible. The international cooperation required for modern cosmology is itself cause for optimism. Scientists from dozens of nations collaborate on these projects, sharing data openly, building on each other's work without regard for borders. The Planck mission was European-led, but included contributions from agencies worldwide. The Event Horizon Telescope that photographed black holes combined observatories from Chile to Hawaii to Antarctica, requiring precise coordination across the globe. These collaborations prove that when we focus on shared goals, understanding reality, pushing back the darkness of ignorance, we can overcome the divisions that plague other aspects of human civilization. The transparency of modern cosmology builds trust. Data is released publicly. Papers are peer-reviewed and debated. Errors are corrected openly. When the BICEP2 team announced detection of primordial gravitational waves in 2014, only to later acknowledge the signal was likely from galactic dust, the scientific community responded not with scandal, but with recognition that this is how science works, through careful checking, through skeptical examination, through the collective process of error correction. The self-correcting nature of science, its willingness to revise conclusions when evidence demands, is a feature, not a bug. And what we've learned is astonishing. We've determined the universe's age to within 1%, approximately 13.8 billion years. We've measured its expansion rate, mapped its geometry, identified its major constituents. We know that ordinary matter atoms, stars, planets, everything we're made of, constitutes less than 5% of the total energy density of the cosmos. We've learned humility. Most of the universe is dark matter and dark energy, substances we can detect through their gravitational effects, but don't yet understand. This ignorance is cause for hope, not despair. It means there are still profound mysteries to solve, fundamental discoveries waiting to be made. When we finally understand dark matter and dark energy, that knowledge will revolutionize physics as deeply as relativity and quantum mechanics did in the 20th century. The fact that we know how much we don't know that we can quantify our ignorance so precisely is itself a remarkable achievement. The question of whether space ends remains open, awaiting better data, improved theories, perhaps conceptual breakthroughs we can't yet imagine. But that openness is exciting. We live in an era where fundamental questions about reality's structure are still being actively investigated and debated. Future generations will envy us the discoveries we're making, just as we envy those who lived through the cosmological revolution of the 20th century. Let's dive into the technical details of how cosmologists actually investigate whether space is finite or infinite, because understanding the methods provides both credibility and appreciation for the challenge involved. The key concept is spatial curvature. In general relativity, space can have three possible geometries: flat, Euclidean, positively curved, spherical, or negatively curved, hyperbolic. A flat universe extends infinitely in all directions, with parallel lines remaining parallel forever. A positively curved universe is finite and closed. It curves back on itself, like the surface of a sphere, but in 3 dimensions. A negatively curved universe is infinite, but has a saddle-like geometry where parallel lines diverge. To measure curvature, cosmologists use the cosmic microwave background. This ancient light, emitted when the universe was 380,000 years old, shows tiny temperature fluctuations that represent density variations in the primordial plasma. These fluctuations have a characteristic angular scale, the typical size of hot and cold spots on the sky that depends on the universe's geometry. Here's the clever part. Sound waves in the early universe created these fluctuations. We know how fast sound traveled in the primordial plasma, roughly 57% of light speed, and how long the waves propagated, 380,000 years. Simple multiplication gives us the physical size of these features at the time the light was emitted. But the angular size we observe depends on the universe's geometry. In a flat universe, distant objects appear the angular size we'd expect from simple geometry. In a curved universe, they appear larger or smaller, just as objects seen through a lens appear distorted. By carefully measuring the angular power spectrum, the distribution of fluctuation sizes across the young cross, sky scientists can determine the universe's curvature with remarkable precision. The Planck satellite's observations indicate that if the universe is curved, the curvature radius must be at least 250 times larger than the observable universe. This means space is either flat or so gently curved that we cannot detect the curvature even when observing across billions of light years. Another method involves observing Type Ia supernova as standard candles objects with known intrinsic brightness. By measuring how bright they appear and comparing to their actual luminosity, astronomers can calculate their distance. If space were significantly curved, the relationship between redshift, how fast objects recede, and distance would deviate from predictions. So far, observations are consistent with flatness. Gravitational lensing provides additional tests. Massive objects like galaxy clusters bend light passing nearby, creating multiple images or arcs of distant galaxies. The pattern of this lensing depends on space-time geometry. Across thousands of observed lensing systems, the patterns match predictions for flat space. Scientists also search for topological signatures repeating patterns that might indicate space curves back on itself. If the universe were a 3-dimensional torus, like the surface of a donut, but in one higher dimension, we might see the same galaxy in multiple directions as light wraps around the universe. Researchers have searched for such cosmic hall of mirrors effects in the cosmic microwave background and galaxy surveys. No conclusive detections yet, but the searches continue with ever-improving data. The challenge is that all these methods probe only the observable universe, the region from which light has had time to reach us. If space is finite, but much larger than our cosmic horizon, we cannot detect that finitude. Our measurements would consistently suggest flatness, even if the universe is actually closed, simply because we're observing too small a region to detect the gentle curvature. Think of an ant on Earth's surface. Measuring triangles and parallel lines across a meter, the ant would conclude the surface is flat. Only by measuring across kilometers would the curvature become detectable. We're in an analogous situation. Cosmically, our observable region might be too small to reveal the universe's global geometry. This limitation means the question, is space infinite, might be observationally unanswerable. We can keep improving our measurements, constraining the minimum size of space as finite, but we cannot definitively prove infinity. The best we can say is, space is either infinite or larger than x, where x keeps growing as our observations improve. Yet even this constrained knowledge is valuable. Knowing that space is at least hundreds of times larger than the observable universe tells us something profound about our cosmic context. And the methods themselves, the sophisticated integration of observation, theory, and mathematics, represent some of humanity's finest intellectual achievements. Looking forward, what new observations or theoretical developments might finally settle the question of whether space ends? What missions, what technologies, what breakthroughs might we expect in the coming decades? The next generation of cosmic surveys will probe larger volumes with greater precision. The Vera C. Rubin Observatory, beginning operations soon, will survey billions of galaxies, mapping the large-scale structure of the universe in unprecedented detail. If space has a complex topology, if it wraps around itself in ways that create correlations in galaxy positions, such surveys might detect those patterns. The Square Kilometre Array, a radio telescope network spanning continents, will map neutral hydrogen across cosmic history. By observing how matter was distributed at different epochs, scientists can test cosmological models with new precision. Any deviation from predictions for flat, infinite space would stand out in such rich datasets. Gravitational wave astronomy, still in its infancy, offers entirely new ways to probe the cosmos. As detectors improve, we'll observe collisions between black holes and neutron stars across most of cosmic history. The properties of these signals, how they're affected by the universe's expansion and geometry, provide independent tests of cosmological models. An unexpected pattern in gravitational wave data might hint at finite space in ways electromagnetic observations miss. Perhaps most speculatively, advances in quantum gravity might finally unify general relativity with quantum mechanics. Currently, these two pillars of physics are incompatible at extreme scales, the Planck length 103.5 meters, where quantum effects and gravitational effects become equally important. At such scales, space itself might be discrete rather than continuous, made of fundamental units that cannot be subdivided further. If we develop a successful theory of quantum gravity, whether string theory, loop quantum gravity, or something yet undiscovered, it might make definite predictions about space's global structure. Perhaps quantum effects mandate finite volume, or perhaps they permit only infinite space. The answer would come not from observation, but from theoretical consistency, from the requirement that physics remain self-consistent at all scales. Some speculative proposals suggest we might detect boundary effects even from within a finite universe. If space has a complex topology, quantum fields might show subtle signatures, vacuum energy patterns, or particle behavior that reflects the global geometry. These effects would be extraordinarily difficult to detect, requiring precision far beyond current capabilities, but they're not impossible in principle. The search for extraterrestrial intelligence, while not directly cosmological, might provide surprising insights. If we ever receive signals from an advanced civilization, their cosmological knowledge could far exceed ours. They might have been observing the universe for millions of years, from locations separated by thousands of light years from our vantage point, giving them perspectives we lack. Their understanding of space's structure might settle questions we're still debating. More fundamentally, perhaps the question will eventually be recognized as wrong, not wrong in the sense of incorrect, but wrong in the sense of malformed, based on misconceptions about what space is. Just as asking, "What's north of the North Pole?" reveals a misunderstanding of spherical geometry, perhaps asking, "Does space end?" reveals misunderstanding about the nature of space itself. Maybe space isn't a pre-existing stage on which matter performs, but an emergent property of quantum fields, something that exists only where and when matter and energy create it through their interactions. Maybe space is observer-dependent, its extent determined by observation itself. Maybe space is computational, existing only where calculated by some substrate of reality beyond our comprehension. In any of these scenarios, does space end becomes the wrong question, replaced by inquiries about how space emerges, what creates it, what maintains it. The honest answer to what comes next is, we don't know. That's not a failure of science, but an acknowledgement that we're still exploring, still learning, still pushing the boundaries of understanding. Every decade brings surprises, dark energy, accelerating expansion, gravitational waves, exoplanets, none of which were anticipated by mainstream cosmology before their discoveries. The next decades will certainly bring their own surprises, observations that challenge current models and force us to expand our conception of reality once again. As we reach the end of this journey through one of cosmology's deepest questions, let's take a moment to reflect on what we've explored and what it means for how we understand our place in existence. We've confronted the possibility that space might end, whether through geometric closure, through topological boundaries, through edges we cannot reach, or through conceptual limitations we cannot transcend. We've explored reassuring facts that any such boundary would be so remote as to be irrelevant to our cosmic neighborhood. We've ventured into speculation, simulation hypotheses, contracting universes, observer-dependent reality. We've grounded ourselves in the scale of the cosmos and the mathematics that let us probe its structure. What emerges from this exploration is not certainty, but nuance. Space might be infinite, extending forever in all directions, making our observable universe an infinitesimal sample of an endless cosmos. Or space might be finite, but unimaginably vast, curved back on itself in ways we cannot yet detect, but may someday observe. Or space might end in ways we haven't imagined, ways that require conceptual frameworks we haven't developed. The question, does space end, might ultimately be less important than the journey of asking it. In pursuing this question, we've pushed the boundaries of physics, developed extraordinary observational tools, united in international scientific collaboration, and contemplated our existence at the deepest level. The question serves as a catalyst for discovery, regardless of its ultimate answer. There's a profound humility in acknowledging that we might never know for certain whether space is infinite or finite. Despite our sophisticated instruments, our elegant mathematics, our centuries of scientific progress, the cosmos might harbor secrets permanently beyond our reach. And that's okay. Mystery isn't a failure, it's an invitation. Every unanswered question represents potential for future understanding, inspiration for coming generations, motivation to keep exploring. But there's also wonder in what we do know. We know the universe is at least hundreds of times larger than we can observe. We know it's been expanding for 13.8 billion years. We know it contains structures of breathtaking complexity and beauty galaxies swirling in cosmic dances, stars forging elements in their cores, planets orbiting in the vast darkness. Whether space ends or continues forever, whether we inhabit a finite cosmos or an infinite one, these wonders remain. For those who find infinity comforting, who draw hope from boundlessness, who see in endless space the promise of infinite possibility, the evidence suggests space might well satisfy that hope. The measurements point toward flatness, toward infinite extent, toward a cosmos without boundaries. For those who find finitude meaningful, who seek the comprehensible over the endless, who draw comfort from limits and definition. The evidence doesn't rule out a closed universe, just makes it very large if it exists. Perhaps the deepest insight is that our existence doesn't depend on the answer. Whether space ends or continues forever, we're here, conscious minds contemplating the cosmos, capable of asking these profound questions and pursuing answers. That consciousness, that curiosity, that drive to understand, these matter infinitely more than the universe's geometry. So good night to infinity, or good night to finitude, or good night to whatever strange hybrid or alternative we eventually discover space to be. Good night to the observable universe, that 93 billion light-year sphere filled with 2 trillion galaxies. Good night to the cosmic microwave background, that ancient light carrying messages from the universe's infancy. Good night to the dark matter and dark energy that constitute most of reality, yet remain mysterious. And good morning to the questions still ahead, to the observations yet to be made, to the theories waiting to be developed. Good morning to the next generation of telescopes that will probe deeper into space and time. Good morning to the scientists and philosophers who will continue this investigation, building on what we've learned, pushing further than we've reached. Before we part, I'd love to hear your thoughts. Does the idea of infinite space comfort you or overwhelm you? Does a finite universe feel constraining or comprehensible? What aspect of this cosmic question captivates you most? Drop your reflections in the comments. I read them all, and these discussions are often where the most interesting ideas emerge. If you found this exploration valuable, if it challenged you or taught you something, or sparked your curiosity, please like the video and subscribe to the channel. There are so many more cosmic mysteries to explore together. The question of whether space ends will continue to haunt and inspire us. It represents the frontier of human knowledge, the boundary between what we understand and what remains mysterious. And in that boundary, in that twilight zone between knowing and not knowing, we find perhaps the most human part of a scientific enterprise, the willingness to ask questions whose answers might forever elude us, simply because asking matters, because understanding is its own reward, because we are creatures who cannot help but wonder about the cosmos we inhabit. Sweet dreams, space travelers. Whether space ends or extends forever, whether we live in a finite cosmic container or an infinite expanse, we share this moment of existence together, conscious witnesses to the universe's grandeur, temporary patterns of matter and energy, lucky enough to contemplate reality itself. That's not just wonder, that's privilege beyond measure.